Welcome back to Particle Physics and the Standard Model. This is lecture 30. And last time we saw how to construct a Yang-Mills theory, which is nothing but a gauge theory with a non-abelian group, right, as your internal symmetry. And we characterized the unitary matrix in terms of an exponentiation of the function that generates the matrix and the generators themselves, right? And we saw that you needed a structure constant that gave you the Lie algebra of the generators of the unitary group, correct? And the structure constant uniquely determines what group you are talking about, right? And we went on to construct the kinetic term for both the field under which you have this gauge transformation, I mean the field that transforms under the gauge symmetry, as well as the gauge boson itself, right? And we saw that the non-trivial thing was that the field strength tensor had this extra bit that gave you self interactions among the gauge bosons that gave rise to vertices such as these 3 boson vertices, 4 boson vertices, and so on, which we saw already in QCD as well as in the weak interaction, correct? And one other thing we saw was that the number of generators is forced to be the number of gauge bosons, rather the other way around. The number of gauge bosons that you have is forced to be the number of generators, and we saw that that is because the gauge bosons actually live in the adjoint representation of the group. And we were on our way to see what the adjoint representation meant. So I started writing the infinitesimal transformations under in the fundamental representation, right? So this is where we saw that you have a set of generators for the fundamental representation, you have another set for the anti-fundamental representation, and we finished by saying it's completely possible for you to have another set for the adjoint representation as well, okay? So in general you would put the representation's name as a subscript. So if you don't write anything, it's understood that it's by default in the fundamental representation. Okay. Now you can see a lot of indices floating around here. Let's just clarify one more time what they mean. Okay. So the A, B, etc., right, that you see up here, here and here, those correspond to the Lie algebra generator index. And when I write I, J, that corresponds to, we already wrote it here, that corresponds to the actual degrees of freedom that are transforming under the SUN, but we can give them some names. We already gave them some names already, right, in the very first lectures. This is what we mean by color for the SU3, weak isospin for SU2, that is the weak force, and so on. Okay, so that's what this is, and this would be a good time to introduce you to another set of generators in the fundamental representation. Okay, so we already know that for SU2 the generators are the polymatrices, right, and that satisfied the relation this, correct? So that the structure constant is the Levi-Civita tensor, antisymmetric Levi-Civita tensor, right? For SU3 Okay, what are the generators called? How many generators are there? 8 generators, 3 square minus 1, remember? And the generators are called the Gell-Mann matrices. I'm sure people before Gell-Mann knew about this, but he's the one who brought all this into physics. Okay, and it's worth looking at the Gell-Mann matrices. Okay, I'll just write it down. The first one is nothing but, the first Pauli matrix and a 0. So this is a 3 by 3 matrix. Okay, keep that in mind. So you have a 2 by 2 block with the Pauli matrix 1 and then the 0, and the second one and the third one are the same. That's not a sigma square. That's a second Pauli matrix. Okay, so I apologize for putting an index in the superscript. I could have used a subscript, but then we are using superscript all over the place anyway. That's the reason I'm putting it there. These are not powers, okay? Now, lambda 4 happens to be this, okay? It's a bit like gamma 0 in the wild basis, right? And then lambda 5, okay, you can sort of see a pattern here. Lambda 5 is this, lambda 6 is starting from lambda 6, once again you go back to the Pauli matrices, and lambda 7 is 0 on the Pauli matrix, and lambda 8 is a bit unusual. It's like the third Pauli matrix. It has 1, 1, minus 2. Okay, so these are the generators of SU3. One neat thing you can already notice is that the SU3 seems to contain the SU2 inside, right? In this block diagonal form, correct? And in a sense, it contains the SU2, over here as well, actually, right? So you have terms like this and this. You have it seems like partially you contain SU2. So all this is not a coincidence. Okay, SU2 is indeed a subgroup of SU3. Okay, so we won't be using subgroups very much in this course, but just remember this. Okay, all right. Now, this was possible the way I wrote this. I could have just scaled this up by any factor I wanted, right? All these matrices could have been scaled up by some multiplicative factor. So we have to follow a normalization convention. And the convention that we use is this. Delta AB, okay, that would just imply if I take the trace of TATB, I get a delta AB over 2. You can go check this. Take these 8 matrices and this can be very easily checked, especially with a computer program, right? This can be trivially checked for Pauli matrices. You can already see what it is. You know the commutation anti-commutation relations. But this is how we normalize to get the structure constants. Okay. Okay, excellent. Now we can go on to what we mean by an adjoint representation. I'm not going to go too much into detail, okay, just enough to give you a flavor for this so that we can do particle physics with it. Okay. These are transformations, okay, in the vector space inhabited by the generators themselves. Okay. So what does this mean? The generators, right, themselves actually live on a vector space. They have their own algebra, right? So the matrix elements, remember the U's live in, the SUN space, all these U's. Okay. But the generators actually span their own space. Okay. Take it, if you think of it if you take the generators as abstract entities, okay, don't think of them as matrices at this moment. Just take them as abstract entities that satisfy this Lie algebra. Then they inhabit their own kind of vector, their own vector space. Okay, and if you have transformations within that vector space, that's the adjoint representation. This is exactly why, okay, since you have a vector space with 8 different directions or 8 different dimensions if you want, right, that's why you have n square minus 1 dimensions in this representation, and so n square minus 1 gauge bosons. Okay, and the really interesting thing now is that what are the generators in the adjoint representation? Remember, I just said you can have generators in every representation. In the adjoint representation, the generators are the structure constants themselves. Okay, so see, now I am labeling with an A, not only with just one A, but also with the B and the C. Right? So it does come with all these indices. Those are the generators. Okay, so let's give an example. SU2, simplest example, right? I have how many generators? 3, right? I have 3 generators in the fundamental, but then it's the same that I get for the adjoint as well, right? Because I have 3 structure constants, right? And that gives me, if I were to construct what the generators are in the adjoint representation, it will just be 0, 0, 0, minus I, and the rest are 0. Okay, so here I have a 0, 0, 0 again, an I here, minus I here. And the third generator here would look like, this is not like the Pauli matrix anymore, right? You can see there's a clear difference between how we write these generators and the fundamental representation generators, correct? Okay, excellent. And of course, one other thing worth writing down is that even these generators have commutation relations. Okay, it's very easy to see what this is. It's just the structure functions again, the structure functions that we saw earlier. Okay, because why is that? Because these are still representations of the algebra. Okay, remember the difference between algebra and group? With algebra you can do additions also, that's what we are doing here, right? So the generators are representations of the algebra. Okay, so if all this seems abstract, don't worry about it too much. This is just to show you that there is an underlying mathematical structure to what we've been doing here, okay, for gauge transformations and so on. Okay. The consequence of all this is that in an adjoint representation, okay, it is natural that the transformation of the field actually looks like this. Okay. If you take the infinitesimal limit of this, that's what we get as, you know, transformations like this over here. Where do we write? Over here, right? So this is the infinitesimal transformation, but literally in an adjoint representation, the consequence of having this structure is that fields would transform like this. Okay, so let's just write down that's the adjoint transformation, and to contrast that again, the simple fundamental transformation. So both of them have to work together for us to get a nice gauge invariant theory. Okay, so I'll just write that down. So both of them together have to give me the covariant derivative in such a way that, you know, I have this. Under gauge transformations, what happens? It goes as u d mu phi. So I need both representations. That's the idea here. Okay. Okay, good. So now we have all the ingredients to go on to construct the standard model. Okay, we now have all the mathematical ingredients. We can now write down which of these different elements that nature has made use of and in what combination it has put together to give us the Lagrangian. Okay. Now before we even get to that point, there is one consequence, one physical consequence that already should be intuitive from this non-abelian structure that we've written. Okay, so let me start with that before I write down an actual Lagrangian, just to warm up. Okay. So remember that we said that the strong force becomes weaker at large distances. I am sorry, at small distances, which is a counterintuitive thing, right? You bring two quarks closer, the force becomes weaker, not stronger actually. Everything else that you can think of, the force gets stronger, right? Gravity and electromagnetism. But you pull two quarks apart, the force gets stronger, and this is exactly why we've never isolated free quarks, right? And what was this called? Griffith's chapter 1 or 2 must have talked about it. This property is called asymptotic freedom. Remember, one way to represent that is you can take the strong force, the coupling of the strong force, let me just write it as GS, okay, and as a function of, let's call it energy, okay, but and remember this is all in log space, okay. If I go to lower energies, it means I am talking about larger distances, right. So the strong force goes like this. This is what we mean by asymptotic freedom. If you go to the highest energies, then it becomes feeble enough that you can actually, that is exactly where the quarks become free in a very unusual way, right. So now we see now we can see that this sort of behavior is a direct consequence of having a non-abelian theory. Okay, just from all this structure, we got vertices like these, and we'll see shortly how you get asymptotic freedom as a direct consequence. Okay, here's an intuitive picture of that. Okay. So for that, let's try to remember the concept of charge screening. Remember charge screening in electromagnetism, Debye screening as an example, right? So what is the screening here? So if I had an electrostatic potential due to a test charge, right? Around it, what happens? I polarize the field around it, correct? Yes? And this is what leads to the screening effect, right? If you see from far enough away, right? A distant observer, would see a screening effect because of all the polarized charges, right? Okay, good. Now, roughly, how do we understand this from a quantum field theory point of view? We say that the screening comes because the field is represented by the photon, correct? The photon in the vacuum, okay, in the lowest energy state, in the zero particle state, keeps splitting into fermion antifermion pairs as long as the fermions are charged under electromagnetism, right? What is this diagram called? I've given you all the words here. This is literally the vacuum polarization diagram. Okay, even the lowest energy state, which is the vacuum, contains all these photons and gluons and so on. Okay. So even the vacuum, because of quantum fluctuations, because it's there in the Lagrangian, they will keep splitting into electron-positron pairs or fermion-antifermion pairs, where the fermions and antifermions are virtual particles. Okay. So that is what manifests itself as the field basically splitting into plus and minus charges. Okay. All right. So put differently, the E field effectively diminishes at large distances because of this effect. Okay. But what's the difference with QCD actually? The difference is that it's not just QCD, also SU2, right? Any non-abelian theory, but I'm going to draw it for QCD. In QCD, I do have a vacuum polarization, absolutely. Okay. Again, these are quark-antiquark pairs in this case, right? But notice that because I have these other vertices, right, I can also write another vacuum, I can also draw another vacuum polarization diagram like this. This is a 3 gluon vertex, right? So I can complete the picture. So this is also there. What else can I draw? I can make use of the 4 gluon vertex now, right? And I can absolutely draw this also, which was not available to me in QED, because I didn't have a 3 photon and a 4 photon vertex. Sorry, this is in QCD, right? So what happens here? Okay, let me draw yet another picture to show exactly what happens. When I had charge screening, what was really going on was that, let me redraw it in the middle. What was really going on was I had a field put out in this direction, right, by the test charge, by the central charge. However, the screening was acting in the opposite direction, right? Agreed? From all these positive and negative charges, right? So this acts in this direction. That's how I ended up with a screened charge, right? So electromagnetism, screening. But what is the difference now with QCD? In QCD, let me draw yet another picture. Okay, now I'm not going to draw all the lines. Okay, I still have this. Okay, I have some screening basically from vacuum polarization diagram like this. Okay, this still leads to screening. Okay, but now you also have polarization from gluons themselves, right? So if you think about it, would the gluons actually screen or anti-screen? Would it enhance the field or diminish the field effectively? It would of course enhance the field, right? Even when I'm splitting a gluon, I'm getting two gluons out of one gluon, correct? In other words, the gluons, since the gluons themselves carry a color charge, the effect of the gluons, I'm going to draw that in orange, the effect of the vacuum polarization from the gluon vertices is to enhance the field. See, the orange and the red add up here, right? So this is anti-screening. If you want, you can call it enhancing. Okay, so there is competition now between the gluons trying to enhance the effective field and the quarks trying to diminish the effective field. Okay, so anti-screening is something that happens only for non-abelian charges. In this case, here the color charge. Okay, so the really interesting thing is, it's not a priori clear which of these two effects would actually win, whether screening is better or anti-screening is better, whether screening is stronger or anti-screening is stronger. So let me just write that down. So which effect wins? Okay, comes from the number of colors, but what else can it depend on? You must have seen this formula in Griffiths, right? It's not just the number of colors, because the number of colors determines how many kinds of quarks I can split off, right? It depends on what that SUN is, but also the number of flavors. Remember, we have 6 flavors of quarks. A gluon doesn't know which flavor to split off into. They all get split off equally, right? So that's what determines this. The number of colors actually helps to enhance the anti-screening. Okay, why? Because if you have more number of colors, I can now put out more number of gluons, right? Whereas the number of flavors only acts on the quarks. Okay, so there's a competition between these two, and we find that so long as you have less than 16 flavors, okay, the screening will win, sorry, the anti-screening will win over the screening, and you get an asymptotically free theory. Okay, and obviously we have only 6 flavors, so that's why we live in a world where you have asymptotic freedom in the strong forces. Okay, let me also mention asymptotic freedom is there also in SU2, the weak force. Okay, we just don't see it because the weak force gets broken. Okay, whereas the strong force doesn't get broken obviously, so we do see it. Okay, good. So let me wrap up at this point. We already saw one little thing here, which is that I just said that despite the profusion in flavors that you have, they all have the same coupling to the gluon, right? This is a point that we've been implicitly making throughout our discussion of gauge invariances. We'll start the next lecture with this point, understand what we mean by universal gauge couplings, and then move on to constructing the actual degrees of freedom making up the standard model. Okay, all right, thank you. See you in the next class.